In this video, I want to introduce you to polynomial functions. So in order to do this, we need to start with a definition. So let me start by writing an equation. So we have f of x, our function f, is equal to a sub n, x to the n power, plus a sub n minus 1, x to the n minus 1 power, plus however many terms we have, plus a sub 1x plus a sub 0. So quite a nasty looking formula. It might not make much sense. So let's really understand it, break it down. This is a polynomial function given a couple restrictions on the exponents on x, which we'll talk about in just a minute. So we have all of our coefficients, the a's, and then we have our variables, the x's. So why do we have the n's in there? Well, we don't know how big of a polynomial we have. So let's take a look at one polynomial function. So let's call it g of x. 3x plus 1. This is a linear equation. We're used to seeing linear functions. But it's also a polynomial function. A linear function is just a polynomial function. So in this case, the 3x plus 1, that's just kind of those last two terms. But what if we want to extend it a little bit? What if we want to get to something like quadratic? So in that case, we'd have h of x is equal to, let's say 5x squared plus 2x plus 1. So we couldn't just stop at the x. We had to keep going a little bit further backwards. So we don't know how many terms we don't have. We don't know what the highest degree, what the highest n is, the highest exponent. So it could be something quite large. Let's go back to f of x. Let's say we have 15x to the 90th power plus 2x to the 45th plus 3x squared. And that's an example of a polynomial function as well. So we don't know what the highest n is if we just want to define the largest, or define a polynomial function. We don't know what the n has to be because it could be any n greater than 0, right? Short of just having a constant function. So there is one restriction on that n. To be a polynomial function, n must be positive and it must be a whole number. And the reason for that, if we take, let's say, 2x to the negative 2. Well, what does negative exponent do? It takes whatever it's attached to, it sends it to the denominator, it makes it flip sides. So in this case, we could rewrite this without a negative exponent as 2 over x squared. The negative 2 is on the x, so x is sent to the denominator. So now because x is in the denominator, this is no longer a polynomial function. This would actually be a rational function. Anytime we have x's in the denominator, we'll talk about these more later on, those are rational functions. So that's why it has to be a positive. And if we think about why it has to be a whole number, let's take 2x to the 1/3 power. We'll remember fractional exponents, what those really are, they're roots. So this would be saying 2 times the third root of x. And so now we have a root function. Root function can't be a polynomial function. Polynomial functions, we have to have x being raised to some power. They can have coefficients. We could have any number of variables, but we have to have that x being raised to a positive whole number. Those would be the keys. Now, I threw out a word a couple minutes ago. I said that the degree. We don't know what that n is, what the largest exponent is, so we have the placeholder n. Well, that n refers to the degree of the polynomial. The highest exponent is the degree of the polynomial. So it doesn't necessarily have to be written first. It could be my polynomial is written a little bit out of order. So let's take a polynomial g of x is equal to 2x cubed minus x to the 4th plus 2 minus 3x to the 9th. So we have a jumbled sequence of exponents. We have the 3rd, we have the 4th, we have actually an x to the 0 power right here. The 2, there is no x there, so it's just the constant value 2. Then we have x to the 9th. So if we look at the polynomial written in its descending form, we would just expect to be able to look at the front, but that's not always true. We have to look for the highest exponent because it could be that the polynomial is written out of sequence. So in this case, our degree would be 9. This is a degree 9 polynomial, the 9th degree polynomial. Another very important term, the leading coefficient. So we know what coefficients are. The leading coefficient is the coefficient attached to the highest degree x. if we look at our general polynomial back up here at the top, if we look at it in general form, the leading coefficient would be the an because it's written in that correct descending form. If we look back at our g of x, though, the equation right here in the middle of the page, we already said this thing was not written in the correct form. It wasn't written in descending order. So we had to look at the last term back there, the 9, to tell us where to look, what the degree was. So we look on that term. And so our leading coefficient, we see the 3 sitting out front, but more importantly, we see a -3. So our leading coefficient would be a -3. So always look for the highest exponent, that gives you the degree, and whatever is attached to that gives you the leading coefficient. Now this is only if these things are written in general form. So we're going to talk more and more about polynomials that are written in factored form. So we might see a polynomial that looks like this. Let's say I'm reusing g of x. Let me switch that one. Let me change it to h so there's no confusion. Call this polynomial h of x. So this one's x minus 1 squared, x plus 2 to the third times -2x. So if we just do a quick skim through this thing for the degree and leading coefficient, we see that 3 sitting there, and we might say, well, hey, that has to be the degree, but that's not true because this one doesn't look like our general form polynomial that I have at the top of the screen. We have x minus 1 squared, x plus 2 to the third, minus 2x in parentheses. And so we haven't to multiply this thing together. We don't see just single terms being added and subtracted. We have things that are factored out, which makes it really easy to find the zeros, the x-intercepts, but not as easy to discuss the degree or the leading coefficient. So really, if we want to see those two items, what we would need to do is we'd have to multiply these things back together. So we'd have to take that x minus 1, square it, FOIL it out, take that x plus 2, raise it to the third power, which means we take x plus 2 times x plus 2 times x plus 2, and then we'd have to multiply through by the -2x. Now, that sounds like a lot of work. I really would rather not do that. That'd take a little bit of time, especially as these exponents, if they got even larger, take even more time. So we're going to kind of take a shortcut. If we think about when we're going to get the largest degree, it's not going to be when the x is being multiplied by the 2. It's going to be when the x's are multiplied by other x's. So let's just consider the x terms within each of the factors. So this first factor, I have an x squared. The second one, I have an x cubed. And the third, I have a -2x. I do want to keep track of any coefficients, so I have that coefficient -2 on the x. I want to keep track of those, but again, I'm going to get the highest degree, not when the x is being multiplied by the 2, but when the x's are multiplying by each other. And it's, if I were to write this x minus 1 squared as x minus 1 times x minus 1, it's the same idea. That's why we have that x minus 1 squared in the next line. X times x there is going to give us the x squared. Now taking this line, multiplying everything together, x squared times x to the third is x to the fifth, times another x is going to give me x to the sixth, and the -2 is the only coefficient. So now we can see that a degree is 6, and the leading coefficient is -2. So these often take a little bit more work. We'll do another one in just a second. Before I get there, I want to discuss one last thing, and then we'll put it all together, the end behavior of a polynomial. Now, we're not just talking about these degrees and leading coefficients just arbitrarily. They tell us a lot. End behavior, what the polynomial's tails are going to look like, is dependent on the degree and the leading coefficient. So let's start with something we know, x squared. We know what x squared looks like. It is a U-shaped parabola. If we think about when it's a positive coefficient, it faces up like we have it here. When it's a negative x squared or -5x squared, whatever it might be, it then faces down. Well, x squared, that's a quadratic, but it's also a polynomial equation. Let's generalize that. X squared, the squared, is a even degree. So even degree polynomials, the ends are always going to move together. So notice in the upper one, we have both ends moving up. In the bottom one, we have both ends moving down. So if we think about the difference between the two, the leading coefficient on the first one was positive. On the second one, the leading coefficient was negative. If we think about an odd degree polynomial that we actually know a couple of them, we could think about the linear just x, or we could think about x cubed. Either way, x cubed we know it looks like this, or like this, again dependent on if we have a positive, redraw that one, if we have a positive or negative coefficient. And so for our x cubed, let's go ahead and generalize this. This is an odd degree polynomial. And it is increasing. The tail goes down to the left, up to the right when the leading coefficient is positive. It's a decreasing function, meaning the tail, when it goes to the left, it goes up, and goes down to the right when the leading coefficient is negative. Now, I've left these things the same pictures as x squared and x cubed, but obviously something has changed. The bit that's changed is the bit that's in the middle. So right now I'm erasing the centers of our x squared u and our x cubed little wiggle shape there. We don't know what happens to the centers, but something's going to happen in the middle. Okay, and that's what changes when the degrees change. So x squared, we know what that looks like. It's the u-shaped parabola. But an even degree polynomial is going to still have that same basic u shape, but in the middle there, it could go really crazy. It might have a lot of little zigs, or it might stay fairly smooth, or it could level out, flatten out a little bit, something like this. We don't know, and that's why what I've done is I've erased the center of my basic x squared x cubed function, and I've just put a little dotted line in there to signify that there's something there we don't know. And that's what we're going to study more of as we get into multiplicities of roots and really study those x and y intercepts. Okay, so let's just do one quick example where we take a look at the end behavior. So I'd like to determine the end behavior for this polynomial. So let's take negative x cubed, and then in parentheses I'm going to have x minus 1 to the fourth 2x plus 1 to the second. So if I want to determine the end behavior, I need the degree, I need the leading coefficient. Well, this is another one of those factored polynomials, so I can't just look at the 4. That 4 is the largest degree, but it's on a factor, not a term, so I need to really multiply this thing back together. Or what we did for our shortcut, we just consider the x terms. So I have a negative x cubed, I have an x to the fourth, I have a 2x squared. Let's multiply these things back together. So negative x cubed, obviously just negative x cubed, x to the fourth. That 2x is all being squared there. That whole 2x was the term inside the factor that I have to square. So 2 squared is 4, and x squared is x squared. So now I can see I have a negative 4 for my leading coefficient. I have x to the third, x to the fourth, x to the second. That gives me x to the ninth. So my degree is 9. My leading coefficient is negative 4. Importantly, it's negative, that's the key. So because the degree was 9, tells me the ends move away from each other in the previous picture that I drew on the previous page. So it's either going to go increasing or decreasing. And because the leading coefficient is negative, it tells me it is decreasing. So my end behavior, it rises to the left, falls to the right. We could draw a little picture like this. It looks somewhat like the x cubed function, but I've left that center blank because I don't know what that looks like yet. That's what we're going to need to continue to study. Hope this helped.